You, Mr. Chairman, could I first check that people can hear me?
Yes, we do.
Yes.
Yeah. I'd like to start by congratulating the candidate, Abhinav Gaur, for a really excellent thesis. This is a challenging area, and your work is covering both the device fabrication, device design, characterization, development of DC and AC models for the impedance, and then understanding the role of defects and taking it all the way through to transistors. So excellent work. And I think that having this metrology now in place certainly helps taking this field further along the path from a promising research area to an application. And also thank you for the clarity of your presentation. Excellent introduction to the subject. I do have a few questions, and I think if we could start, I believe it was on your slide 60, and is it possible to bring this slide back up? Hello, I don't know whether Abhinav, can you hear me? No?
I think he can hear us, but we don't hear him.
Yeah.
He's back.
Can you share the slide again, Abhinav? Can you share the slide? We can see the slide.
Yes.
All right. So thank you. As you showed here in this slide, there is a range of possible origins of the defects that you measure in the dispersion of the capacitance and the conductance. Did you have the opportunity to explore different thicknesses of the two-dimensional channel to assess if the effective DIT is scaling with the thickness of the channel?
Abhinav, you need to unmute.
You're on mute. Yeah.
Sure. Yeah. Am I audible now?
Yes.
Yes.
Yes. Okay. So there was some. It was unintended if we had different material thickness.
Mm-hmm.
So with flakes or some other either bilayer or trilayer material, we did not see a big difference in the DIT. It was more or less consistent, because I'm assuming that if it's coming from the channel, then it is more or less going to do, like, even if you have a thicker material, maybe that's not going to impact it too much if it's from the channel. So
yes, did you I had
it's very it's disconnected. So yeah, basically we did not measure very different thickness variations of the channel for the DIT. Mm-hmm. But we've gone from bilayer to 3 to 5 layers, and there we don't see a big change in the DIT experimentally.
Do you think this could be evidence that the defects are related closely to the interfacial layer between the 2D and the oxide?
That is definitely one of the options, because I do mention that. But given the condition, the state of the channel right now, mm-hmm. It is probably more likely that we are looking at these rather than the interfacial things. So I think they would eventually start playing a role once we have like high quality crystalline CVD growth 2D material. That's when they will start to play a bigger role. But even then, I've seen that point defects are also quite critical. Yes. So point defects like sulfur vacancies and even double sulfur vacancies. So this paper is not our result. It's from another group of people that do make CVD MOS2, and then they find that the sulfur vacancies, even though you have very large grains, these are still dominant. So you see how that will affect in terms of the changing of the defect location, right?
Yes, and seeing an upper band gap DIT
Yes.
as you observe experimentally.
Yes.
Yes. Dang. If for the samples which were transferred from the growth, you mentioned the possibility of and experimental observation of residues at the interface.
Yes.
Do you also see hysteresis when you run the capacitance voltage curves? Did you run the curves backwards to see if they showed a hysteresis behavior?
They show insane amounts of hysteresis. So the thing is, the hysteresis is also, we found it's dependent on the channel length. So this we found by looking at IV measurements. That there was a large amount of hysteresis, which I also discussed in chapter 5 of my thesis. And that we mostly say is either by charge defect, charge getting stuck in grain boundaries, or in the oxide. It's most likely, I think it's more likely to be grain boundaries that where it gets stuck. So if you have a longer channel present, you have a larger hysteresis as well that you sort of see as the effect. In CV measurements, we also performed hysteresis, and that was consistently small. Like only in the first measurement, I would see a larger one because I think there would be some DC charging of the channel and the oxide. But after that, because it's only AC measurements, which is with the frequency which is changing, then you don't see a consistently increasing hysteresis. There, it's pretty small. So it's around 1.1 volt or something like that. It's pretty low.
Thank you. I have a follow-on question to this in relation to hysteresis. Do you see a significant difference in the level of hysteresis between films which are grown and transferred compared to films which are grown directly on the oxide, where you shouldn't have residue reduced residues, I imagine, in this case, of the direct?
Yes, I have not looked at these, like the comparison of hysteresis. First of all, the quality of growth on direct growth is also very different, right? So while the growth on sapphire and transfer leads to higher current performance, you have smaller grains which leads to a lower current performance. So if grains are the kind of reason which would cause this, then you would see an increase. But I have not especially looked into comparing direct growth versus transferred for hysteresis.
No, it's a very good point. You would need to have materials of comparable grain size, which is
exactly
not possible through this approach. So I have a general question in relation to future perspective of two-dimensional materials. I mean, clearly they show very considerable promise with tunability of electronic and optical properties. What do you see at this stage as the main research challenges that stand between the study of the material and future applications?
So again, if you go back to the point of the challenges that I showed, the three major challenges from a 2D MOSFET point of view, I think the most pressing thing is the growth of uniform, thin, crystalline 2D material. That is something that we want. Absolutely. It may not be the most essential case when you're talking about very scaled devices, but then variability might become an issue if you don't have crystalline material, right? So not necessarily, it's not the biggest thing. We also need to figure out how to do a dry transfer or like improve the transfer process, right? So these are the two main things in terms of technology wise, because the rest of the things can still be figured out with silicon, in close relation with silicon processing. From a device point of view, I think we still need to work a lot on the contacts because the contact resistance is still quite high. So people are working on, over here are working on like graphene between the sandwich between the 2D and the metal, or some sort of phase change. Or I mean, people are looking at very different methods of changing the contact resistance. The third is definitely from the point of view of interface that I think we need to enhance our understanding of this edge capacitor and the model further to make a more nuanced picture of what the DIT energy actually looks like. Because only once we know what the DIT energy distribution is, can we start to solve it by some sort of chemical treatments.
Yes.
right? So now that these things are more or less established, now we can go in a loop to like experimental understanding of doing some anneals or some sort of treatments to improve the DIT.
Yes, it's a very good point. I was going to mention at the start, without an appropriate metrology, you really don't know what your
How
process
bad it is.
achieved.
Yeah.
And so now you have this tool to be able to really look at process variations. I better just, with the chair, whether I have time for one more question. I'm not sure whether I'm going on.
Yes, you can, please.
Yeah. You were showing the different variables you can change, such as temperature, bias, AC signal frequency.
Yes.
With the emittance spectroscopy. Did you look at the effect of whether they're sensitive to illumination, your devices, or were all your measurements done in enclosed in the dark?
So when I was taught measurements, I was told that they should be done with everything closed and in the dark.
Yeah.
So I mostly stuck to that. Illumination should have a bigger role when you're looking at direct gap materials more, I think. But even then, I think there is a lot of problem with generation recombination that would happen with light illumination, right? So we usually kept our devices always in dark when we measured them.
Yep.
In bilayer, trilayer, I'm not sure if that really makes a very big difference though, but just to be safe.
Yeah. And just one final question. You interpreted your data in parallel mode. So when you made the measurements, you considered it to be a parallel combination of a capacitor and a conductance. Did you also consider the possibility of looking at other interpretations, series mode, or were all
like this CSRS, right? So actually, what we did at some point, we compared the CPGP with the Z theta, so the impedance and the right. So that is supposed to be like the most basic of these small signal characterization. And from there, when we converted the Z theta to capacitance and conductance, we saw that there was a close correlation, which made us say that maybe this is a right model to go forward with.
A good correlation to your theory, to your
so we compared two measurements, right? We measured CP, GP is what I showed in the thing. And then we also did a measurement of Z theta, so impedance and the phase.
Yes.
So by converting this Z theta to capacitance and conductance, we could see that they were pretty much in line. So what we understood from that was that even if we measure the most basic and convert it to a capacitance conductance, it would be fine. So we just stuck to the simpler method of extracting information.
Yes.
Are you talking about, say, the series resistance effect that also comes in, the CSRS sort of a thing?
So it's just really to clarify what mode you interpreted the data in, but as you've gone back directly to what the instrument measures, which is the impedance and the phase angle, then this is not an issue because that's directly what the instrument measures. So to allow the members of the jury to come in, I'd just like to reiterate, I think this is excellent work. It's brought in a lot more understanding to this field. People have been using, including ourselves, just one or two devices. You've brought in large area growth, which brings in statistics to be able to see trends emerge. It's very high quality work, and it was a pleasure to read. So thank you once again, and I think that's I've completed my questions.
Thank you for your kind words.
Thank you, Professor Hurley. So let's continue with Professor Husa.
Thank you, Mr. Chairman. Can you hear me?
I can hear you.
Okay. So thank you, Mr. Chairman, and I would definitely like to join Professor Hurley in congratulating you with the excellent piece of work you did. Indeed, when you started your PhD, there was not much knowledge about DIT characterization in these 2D materials. And I think you really contributed importantly to these characterization techniques and identification of these defects. It's a really nice contribution. Now, maybe I could start with a question also related to that slide about the sulfur vacancies.
Yes.
Basically, here I have two questions. First question is that, well, at least from theory, there is a paper in the literature that's from the group of COMSA. I don't know if you know that paper.
It's the same. Yeah, it's the same paper from here. Yeah.
Okay, so basically they claim there that the sulfur vacancy should be an acceptor. While you see in a lot of literature that people expect sulfur vacancies to n-type doped MOS2, but they claim from their charge state calculation formation energies that it should be an acceptor. So I'm wondering, in the defects that you characterize, did you identify some acceptor states that could be linked eventually to the sulfur vacancies?
So actually, when we're looking at the experimental results, we're talking about electrons, right? So we are mostly talking about electron being trapped, or so we primarily look at electron acceptor states only. So whatever DIT we observe would be acceptor states.
Okay.
And I'm assuming that everything which is below my Fermi level would be part of donor states. So everything that I'm seeing above the Fermi level would be part of the acceptor states, right? And from what I look at this graph by COMSA and or even other people that have talked about this sort of characterization, it seems that the Fermi level is not above those levels, right? So it should not be a donor level. The charge neutrality level is below these sulfur states. So essentially, they should contribute as acceptor type defects.
Okay, I see. Another question related to that. You're probably aware that Professor Stesmans from our group here is hardly trying to identify these sulfur vacancies by electron spin resonance. Yes. And so far, considering different materials, so exfoliated flakes or CVD grown material, sulfurized MO substrates, he could so far never really identify the sulfur vacancy from ESR, electron spin resonance. Do you have any idea why?
Well, I think so. From what I understand about physical defects on 2D materials based on TEM and all these things, is that we still have beta type and gamma type grain boundaries in our material. So if Professor Stesmans is looking at CVD material, then it is highly likely that there are a lot of beta and gamma type grain boundaries. And they are not specifically sulfur vacancies or something like that, right? They are a broad distribution. They can be anything. They could be antisites or vacancies or interstitials, things like that. So that might end up being showing a broad distribution. I'm not entirely sure how ESR works, to be very specific on why he's not seeing sulfur vacancies. But from our measurements as well, we cannot really distinguish that these are sulfur vacancies yet. We cannot yet distinguish. But we think that they are playing a big role.
Of course, what is important with ESR is that your defect should be paramagnetic to be observed.
Yes.
So if it's already in a charged state, which is different from paramagnetic, it could also be a cause why we cannot see it, of course.
So the fact that in this slide, can you see my slide?
Yes.
So in this slide, the fact that the pink and the blue thing that show the sulfur vacancies, the states, if they show spin up and spin down.
Yeah.
So do they show that it could be measured via a spin? It should be, right? Because they can be separated out.
I'm a bit surprised as well, because I would expect that a single vacancy, so I don't know if this refers to a line of vacancies here or a single vacancy. I'm not sure about the DFT calculations there, but I would expect that a single vacancy should have some spin polarized effect. So the dose for the up and the down spins should be different. And you have a spin polarization induced. So it's maybe not a single vacancy which is computed there, but a kind of line of vacancies as they maybe show in the
TEM
graph there. But something we'll have to check, definitely.
Okay.
I have another question related to the defects that you basically characterized as DIT and the border traps. How relevant you think they are if we consider now devices like MOSFETs or tunnel FETs. What these defects could cause, or what properties of the device would be degraded by these defects? Is it more ion-I-off ratios, subthreshold slopes? What would you expect there?
So transition from off to on is definitely impacted when you have defect states, right? Your off to on, the subthreshold slope will degrade by just charging of defect states.
Mm-hmm.
But at the same time, if you have defect states at a certain gate voltage, you will also have a fewer number of free carriers.
Mm-hmm. Yeah.
Right? These fewer number of free carriers will also interact with these defect states to be scattered.
Yeah.
So there's a degradation in terms of subthreshold swing, but there's also a reduction in the on current because there's a reduction in free carrier density and also a reduction in mobility.
Okay. So
both these things would be affected.
Okay.
One thing more directly, one thing indirectly.
Okay, I see. You would expect also some trap-assisted tunneling
in the case of TFETs, yes.
For example. Okay.
I don't want to go there.
Okay, all right. I was just wondering if you also tried to correlate, or you did also measurements on devices to see if there was some correlations possible between your findings and the transistor characteristics.
In general, there is a good correlation between mobility because we can calculate mobility from both points, from
Yes.
DC IV measurements as well as our AC measurements, right? So there's a good correlation. So if we can say based on that mobility is between 1 to 10 or 1 to 20.
Yes.
It's pretty consistent.
Yeah. Maybe a last question. If you look at your outlook, you mentioned it in your outlook that so you talk about first the interaction between dichalcogenides and boron, hexagonal boron nitride, and you say that it's a good interface. And you mentioned that it would be useful to investigate other 2D dielectrics with a higher or a high K and a large band gap that can offer further improvements.
Yes.
Do you have 2D dielectrics in mind? I mean, materials, examples of materials that would be, interesting to investigate?
Actually, I read a paper on these oxide perovskites, which are like nanosheets, which have extremely high dielectric constant. From what I've been told, they're very difficult to manufacture, right? Like to make them ultra thin. It'll be the same problem that we are facing with growing thin semiconductor. The same problem with thin oxide.
Yes. Yes.
But there's also this 2D silicon dioxide. I don't know. I saw this in one of the Infos presentations. But they talk about like a silicon dioxide structure which is extremely very crystalline and there has no dangling bonds on top and bottom with a dielectric constant of 6 or something. Better than HBN.
Yeah, I see. Okay. All right. Okay. Thank you very much. Yep.
Thank you, Professor Roes. Professor Roeseneke.
Thank you, Mr. Chairman. Can you hear me, Abhinav?
I can, Professor, yes.
Okay. Also, I would like to join, of course, the congratulations of my previous colleagues. I also really enjoyed your presentation. It was a very nice overview. And maybe I could even use some of your slides for my course on semiconductors.
That'll be perfect. Yes.
I have a couple of questions for you. My first question is about the dispersion characteristics that you show on in your chapter 5, figure 5.8, and also the mobilities that you extract from IDVG characteristics, which is on figure 5.14. In these two, so one is for you extract mobility from dispersion, the other you extract them from the current characteristics. And in both cases, you find that the mobility is peaking at 8 nanometer hafnium oxide thickness and is lower for both lower and thicker oxides, 4 and 12 nanometer. And I was wondering if you have thought about what could be the reason for that. Is there a thickness dependence in the scattering mechanisms, or are there different scattering mechanisms acting here? Or do you have any other reason or any other explanation to explain this thickness dependence of the mobility?
Actually, if you look at this, and if oxide thickness was really playing a role, then it should be more consistent. That as we reduce the thickness, either mobility increases or mobility consistently decreases. But we see like a dip over here, and it's only 3 data points. So it's very difficult to say something that it's an oxide based effect. It could also be just that the transfer was slightly off, and then in the 4 nanometer or 12 nanometer case, or there was some sort of interface residue present in these oxides or in these devices, which lead to.
So you don't believe this is a fundamental dependence? This is only scattering or statistical variation?
I don't think we can very confidently say something about the role of thickness of the oxide in scattering or on mobility.
Okay.
It might be playing a role, but the idea is that we can, yeah.
Okay, good. Then another question is about the comparison between hafnium oxide and dielectrics. There you find that the STO gave you much better ID, much better mobilities than the hafnium oxide in chapter, I think it's in chapter 5 as well. Yeah. Still, you did most of your work on hafnium oxide, right? Most of your samples are done in hafnium oxide. Would you recommend STO as a dielectric, or is this again just maybe a coincidence or a statistical or variation, statistical variation? The fact that you have better results for STO than for hafnium oxide. This is a fundamental difference. And would that lead us to conclusions concerning the dielectric, which dielectric to use?
So the reason of going to STO was just because we had found that this is a very high K, and this would be a very nice study to see how much we can get a higher capacitance in MOS2. This was the main idea of using STO, right? Most of our work was focused on hafnium oxide because that's the most relevant oxide currently, if you think about silicon processing as well, right? So good high K, and it's well understood. We found that in STO, there are also certain problems. For example, that there is carbon incorporation in the interface, and there's a very low offset between the conduction band of MOS2 and this strontium titanate. So that in itself is a very bad idea when you're talking about electron transport using STO devices, right? Because you can always have gate leakage very high.
There's no barrier.
Yes, exactly. So that is definitely one problem. In terms of performance, we see that it's pretty good. So which means that maybe there are less number of defects at the oxide semiconductor interface with STO, but I don't think that can be a very good reason to just move to that.
Okay. Okay, then a third question that I have is about your residue layer. So you have shown these nice results, which you also discussed during the primary defense and during our meeting afterwards. And you find that indeed that you have this water and carbon residue interface layers that limits severely your capacitance, your performance also, yes. And also the mobility, I guess. The mobility will also be reduced by this. So my question is this? I mean, what is this? How can you get rid of these layers? Is this a fundamental problem, or is this something that is only related to the, let's say, the immature processing at the moment? Do you have some outlook, some perspective to get rid of that interface residue layer?
I think it's mostly dependent on the on processing. That's the biggest thing right now. We have seen in like different sorts of devices. For example, if you look at the tungsten sulfide, which is directly grown on silicon dioxide, which is in the end of chapter 5, right? Mm-hmm. There we see that because there is direct growth and immediate encapsulation, we can really avoid. I haven't shown that the TEM over here, but you can really avoid any sort of interfacial layer which is present between them. So the main reason why this interfacial layer would come is if I let the oxide or the material out in the ambient, right? If I let it stay during processing. So if I can do some sort of in situ growth and then transfer, very complex things. I understand, like all the materials growth, people will be laughing at me right now. But these are just things flying off, right? But in the end, if we can somehow have a place where we can do all these things without the interaction of atmosphere, so water or carbon, that would be the best case scenario to remove these things.
Okay. Okay, if I may, Mr. Chairman, last question maybe. Let me see, I had one more question about if you look at the mobilities that you extract, especially section 5.3 on dual gate MOSFETs, yes. They are still disappointingly small. So the mobilities that you extract are very, very small. compared to what you extract for the STO devices, and that's what we already discussed before.
Yes.
Do you believe these are real mobilities in the sense that couldn't that be an artifact of the extraction method, that you maybe underestimate the number of carriers or overestimate the number of carriers in the channel, and so you would extract automatically a lower mobility? Or do you think these are really fundamental mechanisms, scattering mechanisms, that are limiting the mobility of these layers, these dual-gated MOSFETs?
So if you look at it from the point of view of just DC characterization, then we end up assuming a certain charge density at the voltage based on the oxide capacitance, right? But in this case, we are comparing simulations, DC simulations with AC CV measurements and DC IV measurements, all of them, right? So using AC CV measurements, we can figure out by low frequency CV how much is the charge density, right? And using that, we are calculating mobility. So I think we can safely, because I also show that how the scalability of the MOS capacitance reduces, right? So the charge density that we assume might not be the actual charge density. So considering all of that, we still get a very low mobility. And I think that's because the interface is very thin, the channel is very thin, and then you have a silicon cap deposition on top. So this silicon cap is used to like make fertile ground for a top oxide deposition, right? But this is deposited using PVD, and PVD is not the softest process to deposit any metal, right? You go for e-beam evaporation or things like that. But by going with PVD, we saw that there was some degradation in material properties as well. So channel properties do also get degraded, and this will also play a role in reducing mobility in these devices. Yes, it's very low. I agree.
Okay, thank you.
Thank you.
Thank you, Professor Groenewegen. Professor De Gent.
Hello, do you hear me?
Yes, I can hear you.
Hello, Abhinav. Well, it feels like redundant, but I'm just going to join my three previous colleagues in congratulating you with the very nice presentation, but also with a very nice thesis. It was a good thing to basically get the work done and report on that, but you also made a very clear presentation about your work. So congratulations on that. Now, maybe my first question is a bit more, philosophical, in the sense that 4 years ago, you basically, or about 4 years ago, you started the PhD with the dream of changing the world by introducing and developing a new material to replace silicon. Now, silicon has been out there for, more than 40 years, and the technology has matured over the years. People have been investing quite some time, money, and research on improving the qualities of silicon. Do you think that 2D materials, if we would invest the same amount of effort and time, will ever reach the status of silicon?
Yeah, first of all, I had no misconception that I would change the world when I started the PhD. But silicon has the advantage that it started a long time back as well, right? So if we are comparing any new material with silicon, we also have to see that it has had a big start, right? A lot of privilege in terms of semiconductor work. But I think now is the time when we are also looking at a lot of different types of applications. Right, so it's not just logic and memory. We are also looking at sensors and other peripheral devices, which need not be as high performance as silicon, right? So if we can somehow figure out, say for display technology or things like that, if we can have a P-type, N-type, and this is such a thin material, and it's very easy to compare with IGZO, right? So if these are the sort of things that we can find new applications for 2D materials, that would be the right step to do. Maybe not to just replace silicon with this, but maybe in addition to silicon. That would be a very nice thing to see.
Okay. With your answer, you actually gave a nice introduction to what would have been my next question in terms of indeed applications. Now, indeed, if you don't target the high performance applications with these 2D materials, but other, conventional or less conventional applications, your work indicated that there are, on the one hand, intrinsic limitations to the material, grain boundaries that are growth related, and extrinsic problems with the material. If you would balance the two, the intrinsic problems and the extrinsic problems, like the carbon layer that was hinted before, which of those do you think will hamper the other applications the most?
It broadly depends on what kind of sizes of devices do you want in those sort of devices, in those applications, right? If you're looking at slightly larger size devices, I think we are pretty much okay with like 30 mobility. So there, the processing becomes the most critical thing. How do we assemble all these things together, which with as less defect or as less interaction with environment as possible? So that is one thing. In cases where you need a higher performance, then we would need to focus more on the intrinsic properties of 2D materials first. So maybe, I mean, there's no need to stick to MOS2. You can go to different sorts of 2D materials as well. This is just the most well-studied thing, so I focused on this. But the idea could be to go on to find other 2D materials that have better sort of properties or better growth methods to grow.
Okay. Now, stealing your mind for a minute, I mean, how would you design an experiment to look at the impact of grain boundaries, or with the work you did? I mean, what can you tell about the importance of the grain boundaries? You said it is the most dominating, yes, but how dominant is it, or how significant is it? You said for the DIT, if I scale to smaller dimensions, then I can measure the DIT, indicating that there's a correlation with the grain boundaries. But can you design an experiment to further elaborate on that?
So when we look at capacitance measurements, we always want larger area devices to get a larger signal, right? So in that case, everything is averaged out. So grain boundaries, point defects, everything gets averaged out to one defect density number at any given energy, right? But in order to understand more specifically how grain boundaries would function, maybe the idea would be to go to smaller MOSFETs, right? So if you make small MOSFETs in the range of a grain size or slightly smaller than grain size, then it's most likely that some devices will have no grains absolutely, and some devices may have some grain boundaries. And their performance comparison would be a useful step to start with. Because this is how people have also done it in case of like other thin film semiconductors like polycrystalline silicon and things like that. So this will also tell us what is the impact of grain. So we know that grain boundaries act as DIT, right? But this will also tell us how one particular grain boundary, which we can also identify using TEM and things like that, would impact in terms of output performance. So if we know that there are a few grain boundaries in our material, then we can really make like hundreds of devices, test them and see whether if one device performs bad, then we know that this is, I mean, contacts would be equally good or equally bad in all of them, but the channel might be specifically good or bad in only some of them with grain boundaries, right? Yeah. So this would be a way to look at those.
So electrically. So according to that reasoning, if I would use a CVD grown material on silicon dioxide, which has smaller grains, multiple grain boundaries, versus using the same process for growth on sapphire, where I have larger crystals, that I should see a measurable difference. Is that what you saw in your results?
The comparison of direct growth was, I think, only done for tungsten sulfide in the end of the chapter, right? All the other ones were grown on sapphire, 2D grown sapphire, and then transferred to hafnium oxide or strontium titanate. So it's not a very direct comparison actually, but we do see that even with very small channel lengths, you know, like 170 nanometers, even then there was such a significant dispersion because of poor mobility. So definitely the grain sizes are smaller, their mobility is worse than compared to MOS2, which was grown on sapphire. Okay.
And then maybe a last question on the carbon. So indeed, you say the carbon layer is a problem. Now, if I use an ALD technique, then I will have carbon residues. If I do an insufficient soak step after the first cycle, then I will have an insufficient hydrolysis of the precursor ligands. Especially in one of the dielectric approaches where you do an ALD soak at low temperature, there will be carbon remaining in the dielectric. Will that give you the same problems as the residues, or?
It could. Actually, the thing with TMA soak is that first we are just doing a long tetramethyl aluminum soak, right? So there is more aluminum, there is more carbon at the interface as compared to the rest of the oxide. So that interfacial layer should also be understood how that really affects. But if the impact of carbon is what you want to remove from ALD process, then maybe switching to some slightly different precursors might also be the way, right? I think, for example, for hafnium, there's like hafnium tetrachloride and things like that, which might have some other problems. I'm not so sure.
I just want to say, and do you think that will solve the problem having residual chlorine there?
Maybe not. The idea would be to definitely go for, at least for MOS2, we see that TMA is not the best way. So some sort of thing which can, like people have used yttrium as a seed layer. So yttrium oxide is formed, which is supposedly a higher K than silicon dioxide as well. So people have used that for characterization, or just hafnium, depositing aluminum or hafnium and then that oxidizing. No, the problem will remain of interfacial layer. It's difficult to remove that, and the best way I would suggest would be to use like some 2D dielectrics, which you can like sandwich already your channel between some 2D dielectrics and then transfer it, so that whatever is happening away from the channel, so we can electron can move in peace.
So I'm glad that, I mean, you helped tremendously on developing the methodology to characterize, and that you left some problems for the generations after you to solve. So with that, I'll give the word back to the chairman. Thank you.
Thank you.
Thank you, Professor again, Professor Afanasiev.
Abhinav, can you hear me?
I can hear you, Professor. Yes.
No, we had plenty of discussions, and in fact, most of the questions I had are already answered. But I still have a couple for you. First question is related to the fact that in your very nice presentation you indicated that silicon dioxide is one of the key elements of success of silicon technology. But if I look at the interfaces between silicon dioxide and 2D materials, I see this one of the worst cases in terms of luminescence quenching, in terms of mobility. Boron nitride makes it much better, and people usually tell, oh, we have very large difference in the density of interface traps.
Yes.
So since you are pioneered the development of interface trap quantification method, my question is, have you seen any systematic dependence of interface trap density on the composition of your underlying oxide? Because you tested several material systems, but I have not seen clear comparison.
The comparison was not made knowingly we did not make comparison, because things are moving around. Like even the 2D material is a moving target, so it's very difficult to say if 2D material in chapter 3 is the same as 2D material in chapter 5, right? Even they are different, so it's very difficult to draw comparisons like this. But your question was whether the impact of different oxides plays a role, right? I think so. By AFM measurements, our roughness in both these materials were very similar. Hafnium oxide was less rough, but like around 0.2 or 0.3 nanometers, which is still higher than silicon dioxide, I understand. Strontium titanate was slightly more rough, like around 0.5 nanometers. The DIT remains more or less consistent in these two devices, but in literature, we also saw that if there is a surface roughness, as the corrugated surface, that leads to a very rough interface, right? And there is the major problem of band gap reduction and expansion was in the valence band. So I would like to say that we are not directly measuring those sort of things. We are mostly measuring things in the conduction band, where we also see some sort of fluctuation, but maybe that's not very strong. So for sure, roughness will have some sort of an impact, but exactly how much is that? I think that's masked still by just property of the channel.
Okay, and then I have second question also related to the numbers of interface traps. Okay. If I look at your results in chapter 4, table 4.1, if I just look at the density of border traps you extract, if I look at density of interface traps, and I just calculate the average distance between traps you observe, it appears to be very close to the same value, around 3 nanometers or so from trap to trap distance, which is actually very close to the radius of Coulomb potential at room temperature. It looks like that your trap occupancy is limited by Coulomb repulsion. Would you consider incorporation of this self-avoiding distribution due to the Coulomb repulsion between charged trap and free charge carrier as a limiting, the Coulomb limit of the trap occupancy?
I have not specifically looked into the Coulomb repulsion effect. I think I would have to read a bit more on that to make sure whether I can fit this into the model or not.
Okay, this is for future generations. Yeah?
Yes, that's a very good point. Thank you.
Okay, thank you very much. Thank you.
Thank you. Finally, the promoters, Professor Dennis Han-Chung Lin.
Abhinav, it's my pleasure working with you. And over the past few years, we've been through quite a few challenges, and also shared quite a bit of good moments together. So, and I've been asking myself, and I've been asking you these questions, right? You must remember these are the questions that I've been asking from the beginning. So what is the scalability, right, of this material system, of this MOS system? And you have already answered, in my view, the stage 1 level. That is, we see this and that kind of limitations based on experimental data and based on our understanding of the physics. So my question would be, in terms of sheet charge density, in terms of transport, what can be a viable strategy forward if we are really hell-bent on extracting or squeezing every single bit of performance out of this material system? What are the possible strategies?
So if you remember the slide of scalability, right, or the figure of scalability, the main thing is to obviously remove all these interfacial residues, somehow get rid of them totally. Even then, theoretically, we are limited by this charge centroid thing, right? So which goes on to like the charge centroid moves away from the interface as you go to thicker materials. So either try to find such 2D materials which have very high mobility, even for one channel. So that by first principle simulations, it is ideal that we just use 1 or 2 layers of material. The second thing would be to also have lesser, like going from a 3D oxide to a 2D oxide should also help. Like that has shown from Tarun's simulations and from everyone's simulations that and measurements that having a flat oxide really helps. And that even helps in terms of the charge density, right? So you might have less number of defects or less number of these potholes present when the electrons are moving. So in terms of charge density, these are probably the things. And then mobility is also improved when you have a flatter, like a flatter channel, right? So in terms of performance, if I only look at the speed of carriers and the number of carriers, and that determines the on-state current. Mm-hmm. So these are the ways to probably go to better performance devices.
So I can think of one example, right? We've all learned about this black phosphorus, and there's certain level of N isotropy in that material. And I don't know if you could comment a bit on that.
Black phosphorus, from what I've heard, based on Yeshwant's experience with that, it's very volatile, and I think it's difficult to control when you're making these things, right? So it's from what I've seen, people have not reported a lot on very thin black phosphorus because it just evaporates. But I think by material property, it's an amazing material because yes, anisotropy is a key thing that it has, right? So very good for tunneling these devices if we end up using it for that. It also has very high mobility, and if I'm not wrong, it's p-type as well, right?
Right. And because the idea of going to higher charge density and using this anisotropy approach can be that along the transport direction you have relatively good mobility and relatively light effective mass, whereas along the z-axis or the vertical axis you have very high effective mass, and then you can pack as much as you could.
Exactly.
Right.
So that would be very useful. Black phosphorus is a very good option if we can encapsulate it as soon as it is made. I think that could be. Everything comes with caveats, so like that's what I realized. If we can do this.
Okay, Chairman, that's all I have. Thank you.
Thank you. And finally, the second, or the first promoter, I should say, Professor Haynes.
Well, actually, I have been discussing this so many times with Abhinav, so I have no further questions at this point of time. Yeah.
Okay, thank you. So this is a public defense, which means that even though this is now organized virtually, you can raise your hand if anyone from the audience want to ask a question to our PhD candidate.
Are there questions?
It seems that things remain silent, which means that this part of the defense is finished. The jury will now retreat for deliberation, and we will be coming back in 15 to 20 minutes. So don't leave the room. We will be leaving this room, moving to the other private room, and then hopefully make it back again. See you in 15 to 20 minutes.
All right. People joining in via YouTube, this is a good time to have chai. See you in 20 minutes.
So Abhitosh didn't have questions?
Oh, Abhitosh didn't have questions.
Yes, tomorrow it's gonna snow.
Yes. Okay. No, I will go out.
We should be getting into the room again. Don't know whether everyone of the jury has yet joined this session here. Assume they do.
I just admitted Michelle, so.
Yeah. Okay. I'm here.
Mark is here.
Okay. Well, then we'll slowly continue with the final part. Dames en heren, geachte collega's, ik geef u kennis van de uitslag van de beraadslaging van de examencommissie aangesteld voor de proef van dokter in de ingenieurswetenschappen. De heer Abhinav Gaur heeft aan de faculteit een proefschrift voorgelegd handelend over Understanding Charge Behavior in a 2D Transition Metal Dichalcogenide MOS System. In het Nederlands, of toch ongeveer, elektronisch gedrag in het 2D-transitie metaal dichalcogenide MOS-systeem. Tot het verkrijgen van de graad van dokter in de ingenieurswetenschappen. En hij heeft dit proefschrift in een openbare zitting voor de examencommissie verdedigd. De examencommissie heeft vastgesteld dat zowel aan de wettelijke en decretale bepalingen als aan de voorschriften van het universiteitsreglement ter zake werd voldaan. Na beraadslaging verklaart de examencommissie dat de heer Abhinav Gaur voldaan heeft aan alle eisen voor de proef en de graad van dokter in de ingenieurswetenschappen behaald. Mr. Abhinav Gaur, the examination board has concluded that you have fulfilled all the requirements laid down in the university regulations for the doctoral examination. Therefore, on behalf of the rector of the KU Leuven, I confer upon you the degree of Doctor of Engineering Science, Materials Engineering. Bij gevolg In de naam van de rector van de KU Leuven wordt de heer Abhinav Gaur gepromoveerd tot dokter in de ingenieurswetenschappen materiaalkunde. De zitting is gesloten. The session is closed. So, Professor Lin, you promised something.
Okay, so I will share my screen and yeah, I will say something. So congratulations, Abhinav, and on behalf of myself and the exploratory device team, we're really happy to have you with us over the past few years. And I don't have a lot of pictures of you, and I do have one. It was taken the moment you learned that you did quite some good work, and that we gave you the go ahead and the green light. So this is something worth remembering. Over the past 4 years, you came from Rochester, and then we worked on the electrical characterization of all these devices, and then gradually build up our story, gradually build up our understanding of this 2D MOS system. And it was quite a journey. There were ups and downs, challenges, but also moments of epiphany. And this really somehow reminds me of a sort of a similar process that I had. You can probably see it as a little story of mine, and I'm trying to picture you. I'm trying to put you also into the story. You know, when it comes to your PhD process. Right? You probably know that I'm a car guy, and I look at things from different perspective, and I see that there's also a fitting PhD story with a specific type of cars that I have, and I think this is a very interesting process for a lot of us in our life. So you have the first encounter of an item or a subject. In your case, it's the 2D materials, and that must have inspired you in some ways, that you want to move ahead, you want to understand the electronic application, you want to know the performance limit of this thing. And then you get into your PhD program, right? It's similar to getting the car, finally, right? Finally own the car, and then there's this first stage of the ownership. This first stage of ownership, you try to explore every buttons and switch of the car. You try to push it to its performance limit. You try to explore all the possible bells and whistles and things that you can do and play around with this vehicle, or in your case, the PhD topic. Maybe 1 or 2 years later, you move to the second stage. Then you start to talk to people really in the know and to see how the car was designed, how the car was built in such a particular way. What was the design philosophy? What were the design trade-offs, for this particular car? And in your case, you learn in your literature survey, you learn through your own hands-on experiment, you learn with all the other experts in the field. You try to figure out why and how and what can we do, with the study, with the material system. And then another 2-3 years pass, and then you enter the third stage. Yeah. So the third stage is, if you were given the mandate to design and engineer to build this car, how would you do so? What kind of knowledge, what kind of resource, what type of breakthrough is required for you to design your own sports car, or for you to design your best device or the best electronic components that will excel in the near future. So over those 3 stages, then you come to the end of the PhD. You are confident that you can build something equally as impressive. You can build something that performs well, and you know all these bells and whistles are good enough. And then one day in the morning, you walk into the garage, you open the door, you see this beautiful car sitting in front of you. And all of a sudden you realize this is not your car. This has never been your car, and it probably never be your car, because this was someone else's achievement. You try to build on top of it. Moving forward, there's going to be some responsibility that you will need to create something of your own, that you will have to share more the responsibilities in terms of scientific research or in terms of scientific engineering, that you have to point the way forward and then build these things rather from even more fundamental perspective, and try to find a better solution or a better material system or a better device design and going forward. You know, so what I'm trying to tell you is that this is just the beginning. This is not the end of the PhD. This is not the end of research, but it opens you possibilities. It gives you a chance to go further in depth to build something that is new, that is revolutionary, and that something is yours, that you will be able to tell your kids, you'll be able to tell your friends, you'll be able to tell your grandchildren that I did something significant in my life. Okay, so that's all from me. And yeah, I think you've done a fantastic job. Thanks a lot.
Thank you very much, Dennis, for your kind words. Thank you. Okay, I think, can I say something? Okay. Dennis, over the last 4 or 5 years, I think it has been really a very nice, an extremely nice journey, thanks to all the discussions and the ups and downs, as you said, and the moments of epiphanies that we have figured out. And even when like the 1 year of our modeling work, which was completely wrong. I mean, we were going at it, assuming that this was the correct thing to do. Yeah. And then suddenly we realized this, and then within the next few months we had to rethink about the whole model, and then suddenly start to fit together. So a big thanks also to Gerben Doornbos, because we had a chance encounter with him in a meeting, and then he pointed this out, and then suddenly it was everything then was starting to click one after the other. Yeah. Right. So I think he was very instrumental as well. All the trainings and the teachings that you have done in the lab, they have been very helpful for me. So thank you very much. All our interactions with Professor Haynes over here in the every monthly meetings, I think we had, Professor. Yeah. Almost monthly meetings, which were if not with the content, but they're always in very different levels of thinking, which pushed me to think beyond what I was like. I went with the problem, and then I was always came out quite motivated about how to solve that problem. There was never an answer to the problem, which was, I think it was a good thing that it forced me to always think of the solution. And I'm really thankful that I have gained the skill set while at IMEC and at KU Leuven. So overall, I think I'm gonna miss Leuven and IMEC a lot when I go from here. I spend 4 years of my life over here, and very instrumental period, I think right now, because this is the most recent. But I will always cherish moments that I've spent over here. Thanks to people in IMEC, all my colleagues, and to friends who are outside in Leuven. Thank you very much for joining for my presentation. Anyone who is in Leuven is please invited to come to Dispuye at 6 p.m. The first few drinks are on me, beverages I should say. And then depends how much, yes, if you keep social distance, yes. Thank you so much for joining for this public defense.
Congratulations.
Yeah, congratulations. I had a little limerick happening.
Oh yeah, yes,
Oh, right.
I'm sorry, yes. The CISC limerick chair.
Yeah, you will sing a song.
Do you want me to do the?
Yes, so I just explain what to people who are not sure. Like limerick is a 5-liner poem which is supposed to be crude and making fun of people. So we usually do this thing at CISC, which is a conference where I met Professor Hurley and also Valerie and Michelle who were there, and it was an absolute blast. And this conference has this tradition of a limerick competition, at which Professor Hurley is the undisputed champion.
Yeah, so yeah, we had great fun reading at CISC. So Abhinav said, could I try and think of a quick a limerick? Now I see if I can share my screen. I'm not sure whether I've got permission or not, but I'll just have a quick look. I don't know whether I can.
But you can just say it.
I'll just say it. Yeah.
Yeah.
So here it is. I'll put my thing back on, and then I can maybe sing it. So here we go. Oh. Will the next ICs be 2D or not 2D? It's a complex maze of questions we see, but at this challenging hour arrived the brilliant Abhinav Gaur to show us the way with a CV and a GV.
Wow. You really are the champion of limericks. I hope we can meet more for CISC and then discuss this even further. If my future boss is watching this, it's a very nice conference, CISC. Maybe we should go there.
Oh, very important. Yeah.
Well, as we learned yesterday from Bob, now you will end up in 2 weeks of quarantine.
Yeah.
Indeed. All right. Thank you. Thank you so much, professors, for joining.
Thank you very much. Congratulations.
Thank you all.
Thank you. Congratulations again, Abhinav. Maybe see you tonight.
Yep.
Yes, Professor. Definitely.
Bye.
Definitely.
Bye.
Bye-bye.
Congratulations. Bye.
Bye.